Good afternoon, everybody. Welcome to another sunny afternoon of organic chemistry, Chem 170, with your host, me, Dr. White. All right, important announcement. Remember, about 10, 15 minutes, give or take, after I end class today, I will send out the email to each of you with the password for test number 3. Ooh, it works today. And uh, you'll have until 1 p.m. tomorrow to take test number 3 and then upload it as a single PDF file. I would highly recommend before you upload that PDF file, look at it yourself and make sure it has all the questions that you answered, like all the ones on the test. I sometimes get students who don't put a page on there, and if you check it first, that won't happen. And that's test number 3. Remember, about a half hour after I end class, about every 2 hours, I'll check my email. And tonight I have my office hours. So if you have any questions about test number 3, feel free to either email me or come to my office hour tonight. That's allowed. All right. And now something even more fun I have to talk about. I have a special gift for you or announcement. What's that? Well, let's go. Hang on while I open up D2L. All right, if you go to the assignments area, everybody see D2L on your screen? Okay. Obviously, you'll see test number 3, today's lab, and oh, look, extra credit project. And this is an optional project. Let's open it up. All right, everybody see extra credit project on your screen? All right, this is an extra credit project. It's 10, yes, 10 bonus points. And how do you get the 10 bonus points? Create a chart that contains 10 organic molecules, which are found in the ingredients list of commercially available products. In other words, anything you can buy. You can use a molecule only once in a chart, but you can get up to 3 molecules per product. That's Dr. White's sneaky way of having you look at more than 1 or 2 things, like 4 of them. And to get full credit for that molecule, which is 1 point, all entries in the row of the chart must be correct. For each entry, record the name of the product, the name of the molecule, and 1 functional group, or the only functional group present in that molecule. Now, be sure to put your name on the chart. What this means is if you have a molecule with more than 1 functional group, you only have to name 1 in there. An example would be the chart would look like this. And if you're not sure how to use with your word processor, I use MS Word. I think most of you do. How to make a table like this, I'll be more than happy to show you during my office hours or after lab anytime, or any other time after class. But product, molecule, functional group, brand X wine, ethanol, alcohol. Now, to make it interesting, there are a few molecules you can't use. Can't use sucrose, ethanol, isopropyl alcohol, acetone, ethyl acetate, propane, acetic acid, or methane. Any other molecule you can use. There's certain products you can't use: beer, wine, vegetable oil, vinegar, gasoline, propane gas, natural gas, orange juice, milk, sugar, butter, anything else can be used. Now note, ingredients must appear on an ingredients list of the product, on the product. They must contain also a functional group discussed in the lab, in this class. The reason I do the second part is because students who in the past, when I've done this and didn't have that, would pick functional groups and get it wrong. Pick stuff you know, and that's why I'm limiting it just to functional. Trust me, you can do this real quick. Now, ingredients must be on a list on the product. That means, you know, bananas have certain ester in there. Well, you can't put down banana, this ester, it's an ester. Why? Because I've never seen a banana with an ingredients label. And Dr. White one summer worked produce in a huge supermarket produce basement. So I know my produce. There's no, I've never seen an ingredient list of all the esters and other components of a fruit or vegetable. But you can find a lot of things real quick. Now, this is due by the end of the day, May 5th this year. May 5th is test number 4 day, that Wednesday. This is important. No late projects are accepted. And you can please upload it as a PDF file or MS Word file. Note, this is an optional project. You do not have to submit it. But if you do, it's like getting 10, yes, 10 points more on any of your tests, or you can think of it as 10 more points on your bottom line, which can never hurt you. For some of you, that might be the difference. Hopefully it's not, but it might, between an A and a B or B and a C. So 10, yes, 10 points. So, do you like that? Do I still have 10 fingers? Yeah, I do. Nope, I don't have 11. Now, this is important. Beware. Not all names on labels are IUPAC or common names. Simethicone, you say, oh, O-N-E ending. Ketone. No, it's not a ketone. Simethicone is a trade name or common name for a silicone compound. Now, in case you're not sure how to do this, use Google or your instructor, and I'll explain that to check structures. To use Google, place the name of the chemical, the ingredient in that product in the box and type afterward the phrase chemical structure. And usually one of the first 3 hits on the page of Google search will be leading you to the chemical structure. Guess what? You know how to look at and identify functional groups and molecule. That's why I play that game, circle and name the functional group, 2 points each. You'll be able to use that. Now, notice it says use Google or your instructor to check structures. Now, this is due the 5th of May. If you want, and I'd highly recommend you do, before it's due, email, don't upload it to the assignment area, email me your project as a Word or PDF, and I'll check it. I'll tell you if it's right or wrong. That way, if you do it, it's not hard to get 10, yes, 10 points, and which is always a good thing. Let me show you how easy it is to do. Everybody see that? Carmex? It's a product you put on your lips in the winter. I've been using it for years. And when you put it on your lips, you know how you have that little tingly feeling? I guess that's the scientific way of saying tingly feeling. And if you look at the list, which, and if we were in everybody read that? No, you can't. But if we were to look at the ingredients, oh, look, it has this compound called phenol, phenol. And phenol has 2 functional groups you could put down, either a benzene ring or call it aromatic, or it's an alcohol. You only have to put down one, not both. And therefore, you can use this. Don't tell the instructor I'm telling you this, but you could put down Carmex, phenol, alcohol, or you could put down Carmex, phenol, aromatic ring, or benzene ring, however you want to put it. And ooh, there's other good things on this label you could use too. Ooh, salicylic acid. I'll let you look that up, but that's it. Now, the thing is, you can only get 3 molecules from a product, which not all. So that means you got to look at least 4 different, come on, finger, get up, 4 different things, 4 different products. Or you can look at more. You can do 1 from each one, look at 10. That's up to you. Another misconception is students, until I told them, no, you don't have to, think, oh, each one has to be a different functional group. No, if you want, you can have them all alcohols or ketones or whatever, or mixture, whatever you want. But it has to be one of the functional groups we talked about. Now, we usually don't think of it as a functional group, but I will let you define alkane as a functional group. So if you have a product that has an alkane in it and it's listed, you can use that too. And if you get them all right, you get 10 points. But it helps if you have me check it before, that way you won't miss out. Now, common problem students will say, how come you only gave me 8? They were all right. I'm supposed to get 10 points. I said, no, you need 10 things to get 10 points. Each entry is a point. If you only put down 8 things, you're only going to get 8 points. And again, this is optional, but this deadline is a hard deadline because near the end of the semester, I'm going to be busy enough as it is. And this is located in the assignment area. And when you're ready to hand it in, upload it to the assignment area. All right, anybody have any questions about the extra credit project? 10 points. The reason I'm doing this is my secret way to have you look at stuff and say, oh my goodness, there are chemicals in here, organic chemicals, and I know what they are. And years from now, if you look at a product and you're not sure, do I really want to use this or will it do what it is, you can look up the structures of the chemicals and also the MSDSs, and you'll have a feel for what you're dealing with, which is a good thing. Any questions? Okay, don't forget, and I'll remind you again, there's a hard deadline on that. All right, everybody see BFT on there, and thank you. All right, we're talking about different types of fats and oils, and the key ones I would like you to know are beef fat, which is tallow, pig's fat, which is yellow and white grease. If you're not a chemist who works in this area, you'd call that, or if you're a cook, you'd call that lard. Now, switch is totally off for this, but I just show you some of the fatty acids that are available or in things we consume. And these are the fatty acids, are the acids that react with glycerin to make fats and oils, the triglyceride. Now, nobody uses IUPAC. They have common names. 12 is lauric, myristic is 14, palmitic is 16 stearic. And this one I've never worked with, so I don't even know how to pronounce it. Arachidicic, chicken, dick, whatever. It's rare. Now, these are all saturated. And remember, saturated means it has only carbon-carbon single bonds in the R group. And this is another way of writing a carboxylic acid, which Dr. White doesn't like to do, so I don't. Now, you can have unsaturated fatty acids, which means the fat is unsaturated, and Mother Nature has only done double bonds. Now, where it says cis here, they're wrong because it can be trans too. Whoever wrote this book, and I know who it is, was not an industrial chemist, but the names are right. And the structures, other than the cis or all cis, is not uh, oleic, linoleic, linolenic, one double bond, two, three. You should know the structure of stearic and oleic. We've gone through that. Now, quick thing. Now we're getting into good stuff now. If you see on an ingredient label and look at some of the things you're doing, even not for the project, you see something like laurate, uh, palmitate, stearate, or a mixture of oleic and stearic is called tallowate. You know, those things usually come from, don't get grossed out now, because it's pure by the time you get it, either beef fat or which is tallow, or yellow white grease, which is pig's fat. And that's is a huge industry. And as I mentioned, on Fridays in the Wall Street Journal are the prices, BF, let's see, FOB. I think it's New York. That means where you not including shipping uh, for both the highest grade of tallow, which is you don't have to know BFT, bleachable fancy tallow, and also the two grades of yellow grease and pig's fat, white grease and yellow grease. Yellow grease is a little cheaper because it's got some colored bodies in there and it's not as pure as white grease. And tallow is more expensive than white or yellow grease. Oh, that reminds me, I have time. I do. Years ago, when I was working, by the way, you're on my home court with fats and oils. You were on my home court with ketones and aldehydes, and you were definitely on my home court with amines and quaternary ammonium salts and amine salts. But anyways, I was working for a company, Unichem Chemicals, which took fat and oil and made it into fatty acids, and then we made it into esters and sold all those products. And we were an international company. And I got a call from the president of the United States. He said, I need your help to work with the purchasing manager. I said, oh, okay, what? He said, well, our subsidiary in the Netherlands is having trouble getting tallow. So we're going to ship them 1 million pounds, a 1 million pounds via deep, what's the right term? Deep tanker ship or whatever, from New York Harbor to Rotterdam. And we got to make sure what we ship them is good. So I had to deal with a company in New York that would take samples and send it back to me, to my lab. And also I'd have it analyzed and they'd analyze it. Then once it got to Rotterdam, I'd have someone analyze it so it didn't get messed up or they played games with us. And it was quite interesting because that's a lot of money to have a ship from, United States to Rotterdam. Now, when we talk about, and the switches off for this slide too, when we talk about fats and oils, if we look at some of the animal fats and things in our daily life, if you notice where it says on the table, and let me ask, everybody see the table on there, 15 point, thank you. If you look here, it says beef tallow. Anybody who's worked in the industry, there's no other type of tallow. But anyways, if you notice lard and, which is yellow grease, white grease, and tallow, here are the percent saturated acids. Here's the unsaturated, again, switches off. But if you look at yellow grease, white grease, lard, otherwise in the tallow, it's a roughly 50-50 saturated, unsaturated. Now, you've heard medical science say olive oil is very good for you compared to things like butter or having a lot of bacon in your diet. And why? Because notice olive oil has almost 90% unsaturated acids, which means the fat or oil in this case is mainly unsaturated. And that's a good thing for your body, we're told. And notice the oils have much more unsaturation in the fat, which when you hydrolyze it, you make these fatty acids, which we then analyze, and that's the difference. Now, one of the things since I've worked in this industry, I thought about when I first started teaching this, how do I give my students, you guys, a real feel for real world? I came up with an idea. It worked quite well. And for tallow, and in real life, this works well too. Yellow grease, it switches on now. Aren't you glad I do that on and off? I hope it helps you. For yellow grease, white grease, and tallow, how do you draw a structure in real life without R's? Well, having worked in this area making steric and oleic, I came up with a good approximation. And that approximation is, well, it's roughly 50-50 mixture, saturated, unsaturated, but I've got three things here, so how can I do 50-50? You can't. So I'll say ROS, and this is my little joke, SOS, save our ship, if you know Morse code, and if you've ever seen the Titanic, which was my favorite movie. But anyways, this tells you if I hydrolyze this, acid and water, and let's use HCl, because what happens, this first ester will give me, as we've done before, this alcohol plus steric acid, which I'll abbreviate now this way, R sub S. This one gives me this alcohol plus this fatty acid, oleic acid, which I'll use shorthand, and you can too. If I'm asking you to do the reactions, if I ask you to give the structure, please don't do this. Use the actual carbons and hydrogens. And finally, the last one will give this plus steric acid. And in reality, it's about a 50-50 mixture. But the key thing I'm trying to illustrate is, if I were to ask this, give the reaction products for the following reaction, and you look at that and say, what do I do? Well, tallow, you now know, has this structure. Now you could also have it two oleic acid or alleil groups and one steric acid group. But I like to do this because my little joke SOS, it helps students remember. And again, let me remind you, I didn't write it up above, but I'll write it here. Remember, HCl is an acid, H+. So in your stomach, you get back the alcohol plus the carboxylic acid you would have used to make that ester. And in this case, again, ester number 1 will give me this alcohol plus steric acid, which I'm abbreviating, you can too on a test like that. Ester number 2 will give me this alcohol plus oleic acid. And ester number 3 will give me this one, this alcohol plus steric acid. Now, on the questions, I never asked you to balance it. Therefore, what are the products? I've already done it. It's glycerin, stearic acid, and oleic acid. So I don't have to write anymore. You don't have to write the names down. But for those of you who want to watch closely, if you want to put a 2 there because it makes you feel better, you can. I wouldn't, because what are the products when you hydrolyze acid hydrolysis of tallow? You get glycerin, stearic acid, and oleic acid. And approximately the oleic to stearic acid, about a 50-50 ratio. And you get glycerin. All right. Now, if I were to ask instead of tallow, white grease or yellow grease, you get the same thing because I'm asking you for this structure, use that for tallow, white grease, and yellow grease. So if I were to ask this, and test, I'd say, well, what would be the 3 products you get? And the answer would be right up here, glycerin, stearic acid, and oleic acid. And if I ask for white grease, you get the same thing. How do I know that? Well, I worked for a company where I was in charge of quality control plus research in North America, and we did that to the tune of about 2 to 3 million pounds a week. It was quite exciting working at those levels. All right, so this is my way of giving you a real life feel for what's happening. And this is stuff we do. We sold all this to companies that you use their products. Next time you look at mouthwash or something like that, and you see glycerin on the label, it came from either beef fat or yellow tallow, white grease, or yellow grease. Next time you use cosmetics, if it has glycerin or it says something like something tallowate or stearate or oleate, and look at your hand cream lotions, it's there. Those all came from yellow grease, white grease, and whatever. Do I have time for, oh, you guys ready for a Dr. White story? When I joined, everybody's smiling, good. I got even a thumbs up. Thank you. All right. I was working at the company that did all this, taking tallow, yellow grease, white grease, and converting it into glycerin and fatty acids. It was Unichem Chemical, and it was located at 47th and Racine. And I'd get there early because they let me start somewhat early, and if there were no meetings, I could leave early, 8.5 hours later. If there were meetings later on, well, I have to stick around. One of the reasons they like me to start early is because if I got there at 6 in the morning and there are problems from people in Europe or our company divisions there, they could call me up and know I'm there. And that made everybody happy. So I got away with that. And I also missed rush hour traffic, which from Schaumburg to 47th and Racine, Dan Ryan and the Eisenhower rush hour was not fair, was not fun. And same thing if I took going home, Dan Ryan to the Kennedy to the toll road. That wasn't fun either during rush hour. I remember one snowstorm, it took me 3.5 hours to get home. But anyways, so I would get there early. Well, it was one winter, and I should tell you, we being Unichem, bought the chemical division that made fatty acids from what was still known as the Darling Rendering Company. And a rendering company is a company that they were the biggest in the United States. They would get the leftover carcasses from any dead animals that were during butchering, slaughtering, that they died before they were actually slaughtered and they couldn't use them then. they got shipped to that. And also from various butchers, the fat they would cut off the meat before they cut it into steaks and everything else. That would get sold to Darling. They'd heat it up. I've been near one of their plants because on site where our plant was, they had a Darling plant with the understanding in 5 years they'd shut it down and sell that land to Unichema. But of all the smells in the chemical industry, the one smell you don't get used to is being downwind from a rendering plant, because they used to keep open carcasses in open trucks in the summer. Oh, awful. Luckily, my office was upwind, so I didn't smell it really. But anyways, one winter, I'm coming into, because I was a senior manager, we didn't park in the parking lot. We drove onto the plant, and they had this nice covered area for our cars. So I drive, the guard knows me, I wave, and he knows my license plate. And I go through, and I'm driving by the fountain down the street, and the plant was almost as big as ECC with its own streets. And I'm driving down, all of a sudden, right in the middle of the street, what do you see? A dead cow, full cow, with its legs like this, frozen. I drive around it and get to my office after I park, and the rendering plant that was still there, I knew the manager there because we took over control of the waste treatment, and they'd mess it up every once in a while. I was in charge of that, and I call and yell at them. And then I'd say, come on, work with me. I don't need this. You don't need it. And anyways, if we get charged, you're going to get charged with a fine from the city. So I call him up. He says, what's up, Dr. White? I said, we got a problem. I said, oh, what, did we mess up the waste treatment plants again? No, that's not it. I was just driving in. Guess what's in the middle of the road on the plant? No, what? A dead cow, and it's frozen. Oh, all right, I'll send a forklift truck out and get rid of it. Thanks for telling me. Interesting way to start your day, driving around a dead cow. But anyways, that's a true story. All right, now let's do the following. Remember, this is the way we're doing yellow grease, white grease, and tallow. And why don't you try the following? And I'm going to help you out because you just learned it, and I don't expect you to memorize it. If I were to ask you to give the products for this compound reaction, what I'm really asking you is that reaction. So why don't you all try it? I forgot to mention, but it will be in my email to you when I mail the password. Next Monday, I will be going over test number 3 answers like I always do for a test in class. I'll take it out of the video though. Also, I guarantee by Sunday, 1 p.m., if not a lot earlier, I will have your test scores for test number 3. Did I say test number? Test number 3 in D2L. And I'll also by Sunday, 1 p.m., mail out to you individually an email with your individual points for each question on test number 3. And I don't know if I mentioned earlier, but did I tell you, other than a little minor discomfort and 2 ibuprofen took care of that briefly yesterday, I don't have any side reactions. I didn't either the first time, thank God. Thank you, Lord. Not to bring religion into the classroom, but I guess I just did. And normally I'd make some jokes and do some strange things. Oh, look, nothing's wrong with me, but unfortunately with the stuff going on with J&J, I don't think that's appropriate. Even though it is very minor, it's good to see the CDC and FDA doing their job. Now that we're, how should I put this politely, have a president who's an adult and believes in science or lets scientists do their job. And when you're done, give me a thumbs up. And Cynthia, thank you for your emoji. Same thing for you too, Anna. Oh, thank you, Cynthia. And the dead cow story is true. It was January, and I think it was about 5 o'clock. And that thing was just like, if you've ever seen Animal House, where they have the dead horse in the dean's office, and they were going to shoot him, and they scared him, and he's that. Oh, that was true. Not a fun way to start your morning. All right, I think everybody's done. Let's do this. The question is, what's the product or products? Remember here, I hope you learned it for the test number. If you have an ester, base hydrolysis called saponification, gives you the alcohol you would have used to make that, plus the carboxylate anion of the carboxylic acid you would have used to make that. All right, we have ester number 1. We get this alcohol, plus notice R sub S, so we get sodium stearate. Ester number 2, we have this R prime, which is R sub O, so we get this alcohol, plus, and if you don't put the plus signs in, I don't take all points, plus sodium oleate, the carboxylate anion of oleic acid. And finally, the last alcohol ester, this ester, we get this alcohol, which they're all connected together, which is glycerin, which you don't have to write down, but I will because I know it. And we have sodium stearate. Oops, I forgot the O there, sorry. And you can either put the 2 there, or the 3 products are glycerin, sodium stearate, sodium oleate. And that's how you do it. Now, the company I work for, instead of using acid or base to do a hydrolysis of fats or oils, we use steam, very hot water. Now, in the reactions I just showed you, we use either acid or base to catalyze a reaction. What does a catalyst do? Make the reaction go quicker. It's not consumed, you get it back. Well, what's another way to make a reaction quicker? If you remember from your general chemistry, one way is to heat it. There's a rule of thumb, oh, it's on this thumb, can you see it? A rule of thumb that for every 10 degrees Celsius increase in reaction temperature, the reaction rate doubles. So for certain reactions, instead of using a catalyst, you just heat it higher. Well, that's what we did, and that's why I'm teaching you something that's not in the book, and that's the following. In general, you take steam, and we used high pressure steam. What is steam? Hot water, very hot water. And you get the same products as the acid hydrolysis, except you're not dealing with acid, which is a good thing. So if I take tallow and react it with steam, what am I actually doing? Remember, steam is hot water. And underneath where I'm writing hot water, I will not give you that on a test. What I will give you is steam. And what happens? The reaction I just showed you up here, ester number 1 gives me this alcohol plus stearic acid. Ester number 2 gives me this alcohol plus oleic acid. And ester number 3 gives me this alcohol plus, if you need to, stearic acid. We'd make glycerin, stearic acid, and oleic acid. And that's how you do it. And we're going to come back to this next week because there's something I want to get to. Saponification, I've already shown you that. This is what I want to get to. Now, how many of you ever heard of hydrogenated fats and oils? And why did they do that? Because, and this is a time for another, yeah, we're going to go a little over, maybe to 5 minutes over the break time, because I want to tell a story and then finish something. And then afterward, we'll do the lab, and I'll let you out early today. Shh, don't tell anybody I'm being nice. Actually, I'm not letting you out early, because if we were in face-to-face, we'd have our test, you'd have the lab, and you'd go home. We wouldn't have a lecture like this, but this way, it seems like Zoom, because I got to do everything, it's a little slower at times by a few minutes per week. But anyways, how many of you have heard of hydrogenated fats and oils? You all have. And when you hydrogenate mainly a oil, you get a saturated compound that the R groups that had double bonds are gone. Because you learned double bond hydrogen, you get CH2 instead of the double bond. Well, that compound you make is a solid or semi-solid at room temperature. And if I put some water in there and some flavoring and some yellow dye, I can sell it to you as margarine. I can make a lot of money, and I don't care if it's going to kill you or not, because that's your problem, because saturated fats are not good for your health. Well, true story, when I was at Unichemo, we were part of Unilever, and senior managers, every year they had this beautiful get-together in upper New York State in this really fancy resort. It was sort of like in the, I forgot what part of New York, up in the real fancy, I can't think of the name right now, but anyways, there were these sort of cabins on the outside, but inside they were very beautiful suites, and each one of us had our own suite. There were 4 in a cabin, and you also had a kitchen there, but they provided all the food. We didn't cook, and we also drank heavy that night, but that's, chemists know how to party. But anyways, first day of the meeting, there are about 100, 150 of us, all the senior managers in Unilever worldwide. And about 10 minutes into the introductory talk by the vice president who was in charge of this whole thing that year, The owner of the resort comes in and says, so-and-so here, I've got an urgent call for you. I'm going to show my age. This was before cell phones and internet and all those other good things you can get people directly. And the guy went running out, and 10 minutes later came back. And 15 minutes later, manager of the resort, can so-and-so come, I got an urgent call. And it happened one more time. And finally, the head of the vice president said to this guy, you know something, you've got a serious problem back in the office. I think you should go back, get a plane, just go back and solve it. Well, it turned out, I learned later on, that guy was the marketing manager in charge of the new rollout for a product from Unilever called, I can't believe it's butter, which is a margarine. And what was the problem? Well, they were going to roll out throughout the whole United States this new product. And they're about ready to ship it to all the grocery stores in the United States and their distributors. Well, it turned out somebody opened a case, took out one of the product, opened the top, and it has that foil on, and it was bulged up. What the heck is causing gas or that to bulge? Well, I can't tell you what was the problem. It wasn't anything serious. And the way they solved it was because they had something like 500,000 units already made. They hired some high school students with syringe needles and popped the top and pushed and got the gas out. And they were still safe. And that way people wouldn't get upset, notice the hole. I can tell you that. But anyways, let's look at the following. If we have hydrogenation of a fat or oil, wrong thing. Quick review. You learned this for test number 1, alkene, catalyst, and hydrogen. You get an alkane. Well, by the way, switch is big time on here. If I take this and react it with, say, hydrogen and nickel, carboxylic acid will not be hydrogenated. It will not react with hydrogen and a catalyst, but a double bond will. Do you break carbon-carbon single bonds? No. So break the pi bond. Each carbon of the double bond gets a hydrogen. And this is what you get. Now, if you notice, I have 7 plus 2 plus 7, that's 16. This is stearic acid. And I started with oleic acid. So let's do something else. And the question would be, what would be the product for this following reaction? And I'm going to let you try it. R sub O, carbonyl hydroxyl, this is oleic acid. And what do you get when you hydrogenate it? Well, I should point out, in oleic acid, this is R sub O, and the shorthand for stearic acid, this is R sub S. And give me a thumbs up when you're done. I see Anna's done and very happy she's done. I love those emojis. See everybody done? All right, you're done. Let's take a look at this. If I hydrogenate oleic acid, what do I get? Well, I just showed you it up there. You get stearic acid. So whenever you see a R sub O, the double bond, this right here, is hydrogenated and becomes, oops, sorry about that. This double bond becomes a single bond, which we can abbreviate from stearic acid, this, which is really this, stearic acid. So oleic acid, and here we get stearic acid. And I actually worked where if we had the oleic and the stearic, we would do this, but I'll tell you this story next week. So now, big drum roll. The $1,000,000 question is, if I take vegetable oil, and let me change this. If I take vegetable oil or olive oil or anything else, you're not going to do olive oil, it's more expensive. And I treat it with hydrogen and a catalyst, say, let's put one down, nickel. What would be the product of that reaction? 3 points each. Your turn. I apologize for getting a little later, but I wanted to get to this point. Then we'll take a break right after this, and I'll get you out early today so you can start on test number 3 if you want to. If not, you can do it later today, and you can just do whatever else you wanted to do. Oh, look at your screen. Hint, hint, hint. And when you're done, give me a thumbs up or turn on your camera and smile. Or don't smile. When I'm in a classroom, I tell students, when you're done, look up and smile so I can see some smiling faces. And they do. But then again, organic chemistry is fun. Why shouldn't you smile? But you didn't think that when you started this class. All right, anybody need more? Everybody? All right, give me a thumbs up if you're done. All right, I think enough thumbs up. Let's do this. All right, what does this do? Hydrogen and a catalyst will not react with an ester. This is the beauty of functional group chemistry. If it's not going to react, it's not going to react. So I have my esters here. Well, if you look up here, the double bond in allyl group, this is hydrogenated, and R sub O becomes a sterile group, R sub S. No double bond. So the answer here, and that is why you get hydrogenated fats and oils, which look like this. And that gives you, I'm going to go a couple more minutes and we'll take our 5-minute break. I'm still going to get you out early today, so take a deep breath. I know I don't usually do this, but anyways, that's why you hydrogenate fats and oils, really vegetable oils and fats too, to make them saturated. You know, this is a good place to take a break. Next Monday, coming attractions, I'm going to teach you how to get clean. In other words, I'm going to teach you how soap works. Next time you wash your hands, your dishes, your hair, your clothes, whatever, take a shower or bath, you're doing organic chemistry. Remember, organic chemistry is everywhere. See, I wasn't lying to you. Let's take about a 5-minute break. Why don't you come back at 2:05? I'll see you then. Be with you in a minute. Oh. All right, let's get going. I better give you the, let's get going. Ooh, the whistle works, got everybody back. All right, let's talk about today's lab. By the way, it's sort of sad because if we were face to face in the lab at ECC, you'd be having a lot of fun. I get to watch you have a lot of fun. But unfortunately, because of the pandemic, certain things get suffered, but at least you'll see it and get to learn about it. Today's lab deals with polymers. And polymers, as you learned a while back, is repeating units of different functional groups joined together to make a macromolecule. Macro meaning big. Now, in today's lab, we're going to deal with three different polymers. The first one is a polyurethane. And the reaction you're going to study is an isocyanate. This is a functional group we didn't talk about in class, but it's an important one. But I had to cut down to the key ones, I think, for what your majors are mostly going to be. So I didn't talk about it, but I can talk about it now. It's the R group on nitrogen to carbon to oxygen carbonyl. And this is sort of like a carbonyl of a carboxylic acid. If you take an alcohol, you can make, this is called the urethane. Carbonyl, oxygen, R group, nitrogen, R over here, R prime and R. And this is a very stable, unreactive functional group, which means you can make very strong, long-lasting polymers. Now, when you make a polymer, you use a polymeric isocyanate, which has more than one isocyanate in the molecule. And the alcohol use a polyol, poly meaning many, OL alcohol, where you have a lot of hydroxyl groups. Usually you use sugar, sucrose, which I'll teach you about later on. And this is how you form a polymer. And like I said, use a diisocyanate, two of them here, and a polyol, a polyalcohol. And you form it. By the way, this is a very exothermic reaction. It gives off heat. Now, in order to make a foam, let me ask a quick question. How many of you have ever made bread? And what is bread? Well, when you heat this stuff called flour with other stuff, you have in there yeast. Most spreads are yeast spreads where you feed it some sugar. So it eats the sugar and it gives off CO2, carbon dioxide, a gas. And when you have the bread, the gluten, now Dr. White's getting a little off, or he's not 100% sure the nomenclature of the terms I'm using, but that makes it's very sticky and it traps the gas in there. And I bet you never thought about it, but bread is really a foam. It's a solid foam. And if you ever take real homemade bread or bread from a good bakery, not the stuff you buy for sandwiches, which I don't like. I like good bakery stuff. By the way, if you've never had challah, you're missing everything in life. But anyways, back to it. If you cut it, you'll see all these little holes in the bread and some bigger ones. And that's from the carbon dioxide that when you cook it, expands. And also before that, you let it expand before you punch it down and everything. But you go online or talk to somebody who knows how to bake to get the particulars. But urethane foam was similar. You have what's called a blowing agent in there, something that traps the gas. And when you make that polymer, it rises just like a cake or a bread. I guess the cakes rise. I guess they do. I'm not sure. Well, anyways. Now, your instructor, if we're in the lab. Now, it turns out the urethane industry and two of the main uses for urethane foam, and by the way, urethane foam can be rigid or flexible. Rigid, hard like wood. Flexible, if you're sitting on a cushion right now, that's a urethane cushion or foam. That's flexible. If you get into a car, which has seats that are not solid metal or wood, you're sitting on a flexible urethane foam. Now, it turns out that a big part of the industry is used for insulation. And to make it, I hate to use this term, make it real, I'll be polite, to make it very easy for people who are not well educated to make the foams, the urethane industry came up with the following. They have what's called an A side, which is the isocyanate. And the B side, which has the polyol, that's the alcohol, polyalcohol, but you also have what's called the blowing agent, a catalyst, which is a tertiary amine, and then to make sure it turns out well, usually have a silicone surfactant. And I have a few patents in urethane foam technology, so I know this. And this is the B side, it's this mixture. And the companies sell an A and B side, and you mix equal parts together. See, I said they made it real simple, and you get a urethane foam. Now, when you're getting a urethane foam, there are a few things you measure. One is called the cream time. And this is when the reaction making a urethane starts. And why is it called the cream time? Because, excuse me, that was a sneeze time. Oh, by the way, Dr. White doesn't like coffee, but still, I'll use the analogy. It got the name cream time is because for rigid foam, which is a good part of, thank you, Anna. But anyways, usually for foam insulation, like in your refrigerator, how many of you ever seen the old refrigerators from 1940s and 50s the walls were like this thick. Now go in your kitchen or somebody else's kitchen and look at your refrigerator and they're that thick. Why are they thinner? Because instead of using glass wool to insulate it, like in your, they use urethane, which is a better insulator. But anyways, you're not going to see that, so you don't care what color the foam is, and therefore they use what's called polymer isocyanate, which is usually as dark as black coffee. And when you put the B-side in and mix it, when it starts foaming, the first start, it looks like you poured cream into coffee. Gets lighter, and that's how it got the cream time. So the cream time tells you when you start the reaction. Now, how can you affect the cream time? Well, add more catalyst will make it go quicker. And the lower the cream time, the faster the reaction is. All right, there's another one. A lot of insulation is made and sold as boards. And there, you're going to make this in a mold. An important thing to look for or measure is the tack-free time. And this is, both of these are measured in usually seconds or minutes. This could be seconds or minutes. And what is the tack-free time? I don't know if I'm spelling tacky right, or sticky. When it's no longer sticky or tacky, which means you can take it out of a mold. And these are things you're going to do. And what you'd be doing is weighing out 10 grams of A side in a cup, the isocyanate, 10 grams of the B side in a beaker, in a hood over newspaper. You'd pour in the B side into the A side, stir it real quick for a few seconds, watch for the cream time. When the light color occurs, we call that the cream side. You'd also feel the outside of the cup to see if it gives off heat. And then after a while, you touch the top with a wooden tongue depressor to see when it's no longer sticky. And then I'd show you where to do this. And I've given you the data here for what you would see. But let's take a look so you can see it real time.
Today we're going to talk about molding foam. Specifically today we have a 3 pound per cubic foot molding foam that we want to discuss some of its attributes. This material starts at...
She's got an A and B side. Oh, wait. Yep. I didn't check. Everybody see the YouTube?
foam. So it's going to expand 24 times its liquid volume to create a lightweight, non-absorbing, closed cell foam that can be easily sanded or carved to dimensional shape. It can be cast as backups or as free fed. But it means fast reaction. Colder means a slower reaction is going to create higher density foam than desired. We're going to measure out equal portions in liquid. In this case, we've had some pre-marked beakers. We measure out part B, and now we're going to measure out part A.
See how dark the A side is?
And then we're going to take a flat spatula, not a round dowel, and we're going to pour one into the other, and we're going to simply mix. And it's important that you quickly scrape the sides and the bottom of the container to incorporate all the A and
See
the
how
B.
it turned
So
white?
they get fully reactive. Doesn't take much. When the material starts to react, it'll form a nice even cream color, and you need to pour that into your mold. For this demonstration, we're just going to do a free rise block of foam so that you can actually see how this material expands. We'll pretty well got it mixed, and it's going to create just a little bit of heat on its own. Again, 72 degrees is the perfect temperature to start mixing that. It gives you about a minute or so of time to actually mix the foam and pour it into the mold. You got to be careful now not to put too much foam into a closed cavity mold, because it does create quite a bit of pressure on its own, and it could warp your mold. So now it's starting to come up. And actually, to demonstrate this, we're just going to let it come up to kind of show you what we call free rise in this. So it comes out.
Watch.
It's going to expand. And within about 2 or 3 minutes, it's going to get to be full hardness. And we'll be able to actually pick this up, carve it, and show you how it's used. It's best not to get this on your hands, and I'm not wearing gloves, but you should wear gloves with this right now, because it loves to stick to human hands. That's about it. Well, it's only been about 5 minutes since we initially mixed our foam. And you can see it's pretty well set. It doesn't stick to polyethylene or propylene plastics, so common garbage bags work quite well as a barrier. But you can see it's durable, and it's fairly lightweight. And as we mentioned earlier, it's easy to carve. Then liquids, it's going to be mixed at a 1-to-1 volume.
All right, the one you're doing in the lab isn't going to flow over like that. If we were doing it, it comes to the top of the cup and makes a nice mushroom like, and it's a lot of fun. And that's the first part of today's lab. Let's go to the second part, and that deals with polyamide polymers, otherwise known as nylon. Now, nylon is an important polymer that's really a polyamide, many amide. As you learn now here, to make it go quicker, instead of using a carboxylic acid, we're using an acid chloride, which reacts a lot quicker with amines. Now, this is going to give off HCl, and I should have this here, and you have a base present, and you form an amide. Now, when the amide, when you start with a difunctional acid chloride and a diamine, you make your polymer. And when a diacid is reacted to polyamide, which we call nylon. Now, the key functional group in nylon is an amide. And let's take a look. First of all, let's go through the procedure. What you're going to do in one beaker, we'll call A, and another beaker we'll call B. In A, you'll put the dichloromethane, and this is the acid chloride, and you'll mix it together. In B, you'll put in the diamine, 1,6-diamine, and you'll also add to B some sodium hydroxide, your base, and you'll mix it. And what you do is have your A, carefully pour your B in the side, not inside. What happens is after it's mixed, you'll have 2 layers, and this interface right there is where your nylon is formed, because that's where the 2 chemicals interact and react. And what you'll do is take a piece of long wire with a hook on it, this interface right here, you'll hook it up and you'll pull it up and you'll wrap it around a beaker and you make nylon. It's way cool. But because you can't do that in your home, I don't know why they have that, but first of all, everybody see YouTube on your screen with the explosion? We don't allow that in our lab. Anyways.
Familiar mushroom cloud snakes skyward.
Okay, this is the aqueous.
Deadly radiation.
And that aqueous solution contains the acid, the diacid. And this is a solution of the hexane diamine that's dissolved in hexane, and hexane is
That's your B beaker he's
so this
using.
solution is going to float on top of the other one. And then where the two solutions come together, the interface between these two solutions is where this reaction is going to take place. How many fingers do I have? Anyway, here we go.
I've got the links in the lab so you can go back and watch it at your leisure.
Another species. Here we go. Okay, so I'm very carefully going to pour this down the side, and then where the interface is, we'll have contact between the diacid and the diamino hexane. And the hexane layer is floating on the top here. But of course, where they come together is where the polymer can be made, where the condensation reaction is happening. So then I'm going to reach in here, and where the interface is, I'm going to pull out some nylon.
We use a wire hook, and this is the fun
See how
part.
much nylon we can pull
You
out.
wrap it around a beaker. He's not going to do it a
There's a meter.
beaker way,
Or so.
but that white stuff is nylon.
2. There are records set for this, and so I think it's actually in the Guinness Book of Records. I'm sure we're going to beat that record today. Where are we at?
And like I say, in the lab, I have you wrap it around the beaker, and you can go for about 3, 4, or 5 minutes getting, I don't know, about 5, 6 yards of this
out of
stuff.
a very small quantity. I only dissolved a few grams of the acid and the
And what you'll do is make it, and the whole lab is just the experience of making it. There's no data you have to take. And that's how you make nylon. Now, the original nylon that was first made was by DuPont, and it was in World War II. A lot of organic chemistry was developed during World War II because our enemies had control the Axis powers, like the Japanese, place where you could get silk, and they wouldn't sell that to us because we were at war with them. So how did you get the material needed to make parachutes for the war effort? They came up with nylon. Now, the nylon, near the end of the war, after the war, the story goes, I don't know if it's true or not, but I've heard it, that the guy who was in charge of doing that or came up with the idea, his wife was upset because she couldn't get any more silk stockings. He said, oh, let me take this stuff we just invented and made her a pair of silk stockings made out of nylon, which became known as nylons, which now be known as pantyhose, or other terms, whatever they call it nowadays. And that's organic chemistry. See, it's everywhere. All right, the last lab, I want to talk about the reaction of alcohols with boric acid. And actually, we use a sodium borate, but I'll show it for, take alcohol, a reactor with boric acid. What you get is called borate esters. And this is a borate ester. And actually, one of my patents, I use borate esters. So I'm quite familiar. Now, if the alcohol is a polyol, like Elmer's glue, there are a lot of them, and N is on the order of about 1 million. When you react this with boric acid or sodium borate, you'll get these long chains that are linked together. And there'd be another chain here. And now you're making really, really large polymer molecules. If R is a polymeric alcohol, if it's a single alcohol, you're making small ones. If you've got a polymer like Elmer's glue, you make big ones. Does that make a difference? Well, that's what you're going to find out in this lab. Let's take a look first at the lab. And here you would take, first lab, you'd mix the boric acid with isopropyl alcohol, isopropanol, a simple alcohol. And when you finish, it's clear. When you take polyvinyl alcohol with the boric acid, you mix together, you get this gooey, slimy white solid, also known as monster slime.
Hi everyone, today I'm so excited to show you our favorite slime recipe.
Everybody
This is
sees the
most
slime on the
amazing,
screen?
softest, gooey, oozy slime, and it's so much fun to play with. First, we will begin by creating our slime activator. You use 1 cup of hot water with half a teaspoon of borax.
And that you get
Make
from
sure
a
to stir well
supermarket.
so that you dissolve all the powder. Once you are done mixing, you can keep it to the side. If you prefer not to use the borax activator, you could also use contact lens solution that contains boric acid. Now we'll start our slime. I'm using 1 part of glue, so 1 bottle of Elmer's PVA glue, and I'm going to mix it with warm water. So I'm going to add the warm water into the glue bottle. Now I'm going to close the top and I'm going to shake it. That will help spread the.
In the lab, we don't use this much, but you still make enough to have fun with.
You can open it up and add it to your mixture. Now just go ahead and mix it all together so that you don't end up with any clumps. You want a nice smooth mixture. I tend to keep on hand a bunch of ice cream sticks because they're the easiest to clean up afterwards and they do a great job of mixing. Then you will add your food color of choice. I choose.
We don't use food color.
Because I like how
Gets on everywhere.
small. You just need 1 drop. I'm going today with a purple color. For some reason, it's looking a bit bluish. I chose purple because we currently have a million different slimes at home. So we've got a butter slime that's yellow. We have 2 fluffy slimes that are pink and blue. You can find the recipes and video tutorials by clicking one of the links. Keep mixing until you don't have any streaks left over. Now your borax mixture would have had time to dissolve. Make sure that you give it a good mix before you start adding it in. This is really important that you add it in really slowly because this is sort of the part that's going to make or break your slime. So I tend to go and add in a teaspoon at a time, and then I mix, and then I can add another teaspoon at a time and mix. You will see that it starts to sticking together. As I raise my spoon, I'll show you. Yeah, see? And I think it's better when you are adding in the borax that you don't just add it to one place, because then just that area is going to get put together. Whereas if you sprinkle a little all around, then it actually you can add in between 5 to 7 teaspoons of borax. The less sticky it's going to get. I love how it just spreads out the minute you put it down. So my favorite thing to add to slime that makes it super stretchy and really soft is to add any kind of lotion that you have. So I just added in the lotion that I had from one of our hotel stays. So it's, wow. When I'm done, I add it to our slime containers. We have a whole bunch of different slimes that we have at home. I normally label it with a sticker.
And for this slab, like we said, you'll be using isopropanol here. And then you have a bunch of questions to ask. And that's today's lab. I bet you never thought I'd get into monster slime. You know, if you've ever seen like the original Star Wars, when that one monster, not the original, the third Star Wars, where Luke is fighting that monster and all that scum and slime is coming out of his mouth, that's that borate ester of Elmer's glue. Now there's ways of using different types, the actual polymer in the Elmer's glue where it comes out clear instead of milky, but that's today's lab. And with that, I'm done. Remember, in a little while, about next 10 minutes, 15 minutes, I'll be sending out the email to test number 3 with the password. You have until 1 tomorrow, 1 p.m. to get it in. Don't forget, this afternoon and tonight, I'll be checking my email. Also, if you have any questions, email me. Also tomorrow morning, early before I teach. Tomorrow I teach at the other school from 9 until about 11:30. So I won't be checking my email then. But I will also have my office hours tonight. When if you have any questions, come on by. And with that, I'll see you next Monday. Gang gesund. Goodbye. Be healthy.